Time to do some trig and log stuff. Sorry about that. That's last year's model. Wrong date. All right. Can we do these things without a calculator? I hope so. So sine of 3. I don't want you to draw in unit circles every single time you need to do some trig. This might be happening in your mind, or in my mind in this case. So 3 pi over 2 is here. Sine is the y coordinate. Negative 5 pi over 6. So we're going around this way. That's like pi over 6 short of halfway around the circle. It's pi over 6 short of a pi. So that would bring me to here. And cosine is the x coordinate, so that's negative square root of 3 over 2. On all these little triangles that we imagine here, they all have sides that are either 1/2, square root of 2 over 2, square root of 3 over 2. Of course, there's the zeros and the ones on the ends of that. Now, if you're looking at something like this, and this is the x-coordinate, that x-coordinate, it's clearly like the bigger leg. So these two always come together as legs of a triangle. So for example, sine of this would be negative 1/2. If you need more coaching with that, let me know. I think that with some practice it can be pretty easy. I've been doing this for a long time. I don't just have them memorized. I just like have a little mental picture of this that I can work through real quickly. And I think that's what I would recommend anyway. So if you feel like, oh, I don't have those memorized anymore, it's probably not a problem. Tangent of pi over 4, at pi over 4 sine and cosine are equal, so that's 1. The cosecant of 5 pi over 4. Cosecant is whatever the sine is upside down. So let's do that. So 5 pi over 4, that's, let's see, pi over 4, that's 1, 2, 3, 4, 5 pi over 4. So the sine of that would be, that's the y coordinate, so that would be negative square root of 2 over 2. So this is negative 2 over the square root of 2. But of course, 2 divided by the square root of 2 is the square root of 2, right? Because that's like the square root of 2 times itself, so one of them cancels and blah, blah, blah. All right, so how about the secant of pi over 2? That's cosine of pi over 2 upside down. So cosine of pi over 2, that is, let's see, the x-coordinate here, which is 0, and then flip that upside down. Ooh, undefined. Can't flip 0 over. How about inverse trig functions? So this is like saying if this is the y-coordinate, then what's the angle? So if you have a y-coordinate of negative 1/2, then what angle are you at? Oh, well, you're there or there, and how do I know which one? Well, you know which one because the sine inverse function, if it's going to be a function, it's got to choose one of those angles all the time. Otherwise, you get vertical line test. Fail. So which one do we pick? Sine inverse, always we choose in between negative pi over 2 and pi over 2. So if we're choosing there, then negative pi over 6 is the winner. All right, what angle has a cosine of square root of 2 over 2? That's an x-coordinate. So x-coordinate of square root of 2 over 2, positive is here. That's pi over 4. How about a tangent inverse of the square root of 3? Tangent inverse of 1 is pi over 4, and square root of 3, that's the bigger one, so that's pi over 3. The tangent inverse of 1 over the square root of 3, this upside down, or the square root of 3 over 3, it's another way of writing that, is pi over 6. That's the one that's smaller than 1, and then at 1 it's pi over 4, and when you get to the square root of 3, well, that corresponds to pi over 3. Secant inverse of 2 is the same as the cosine inverse of 1/2. So let's see, cosine inverse of 1/2, what angle has an x-coordinate of 1/2? That'd be up here. That is also pi over 3. the square root of 2 over 2's with sines and cosines, that's the stuff that goes with the pi over 4's. And these are the ones that go with pi over 6's and pi over 3's. All right, cotangent of this, that's the same as the tangent inverse of this upside down. And I did that, so that's just negative pi over 3. All right. Oh, except for the cotangent function, sorry. That's bad. What's the range of values for the cotangent function? Maybe that's not totally obvious, since cotangent is cosine over sine. We don't want to actually include where this is equal to 0. So we go from 0 to pi. And why are these open brackets? Because we can't include the endpoints. It's undefined there. So we do need that angle, but we need that angle at the place where it's in between here. So I believe that that is 5 pi over 3. That's the right answer. Okay, I would be much more concerned about, want to be able to do these. This, less so, if the secants and cotangents and cosecants freak you out. All right, so if the sine of some angle is 2/7 for an angle in the second quadrant, all right, sine is opposite over hypotenuse, so it'll be an opposite side of 2 and a hypotenuse of 7 for an angle in the second quadrant. Angles, when we're doing things like this, unit circle or whatever, we always want to measure angles from horizontal. Same will go for physics. If you have an angle that for whatever reason is measured from the vertical, we're just going to change it to horizontal, because all of that sine is opposite over hypotenuse, and everything else really depends when you're on a coordinate system. It depends on that the angle, being right next to the axis, the horizontal axis. Okay, so if that's 2 and that's 7, then by the Pythagorean theorem, this must be the square root of 45. You can write that work out if you need to. And the square root of 45 is 9 times 5, so that's 3 square root 5. And since this is the x-coordinate in the second quadrant, that's negative. So what are the other trig functions? So if sine of theta is 2/7, cosine of theta is going to be negative 3 root 5 over 7. Tangent of theta is sine over cosine. The 7's on the bottom cancel out. We get 2 over negative 3 root 5. Is it a problem that there's a square root sign on the bottom? Not anymore. That's a rule that is for babies, not you guys. So cosecant is this upside down. Secant is this upside down. And cotangent is that upside down. All right, I got to sketch some graphs here. Let's see. It says just sketch them, so I'm not going to stress out and go running and looking for some graph paper. You might not have any, so we want to do sine and cosecant on the same set of axes. So let's see. What number is this? 4. So this is a sine function. Looks like this. Try to do 2 periods of it, 1 on each side, and that's 2 pi, and that's pi, and so on, and that's like 1 and negative 1 here. So that's y equals sine x. Ooh, I'm supposed to do, pi x. Now, what does that do? Well, the period of a trig function is 2 pi divided by whatever number is right there. If it's just a 1, then the period is 2 pi. But here it's a pi, so the period here is 2. So, didn't need that pi there. All right, that was easy to fix. Now, we're also supposed to sketch y equals cosecant of pi x. Same thing on the inside. Now sine and cosecant are upside down of each other. So just imagine taking all of the y values of this and flipping them upside down. So for example, 1, when you flip that over, it's still just 1. And then -1, when you flip that over, that's still just -1. Now when you flip 0 over, uh-oh, you got yourself a little vertical asymptote there. So if you flip 0 over, so the y-axis is also an asymptote. And then when you flip over numbers that are smaller than 1, like these, you get things that are bigger than 1, because numbers. So the cosecant function just makes these little doodads. Little parabolas, right? Wrong. They're not parabolas. You study parabolas so much in Algebra 2 that one would get the mistaken impression, not your fault, that every curvy-looking thing like that, U kind of shape, is a parabola. And that is most definitely not true. These things are not parabolas. They can't be, because parabolas don't have vertical asymptotes. So whatever these things are, well, they're pieces of the cosecant curve, they are not parabolas. I think it would be even incorrect to say that they are parabolic, because I think parabolic in the world of math really means something more literal. It really means something is a parabola, if it's parabolic. So what are those things? They're pieces of the cosecant curve. We don't need to say anything more than that. All right, number 5. We've got 2 cosine x over 2 and 2 secant x over 2. So what does it do when we have something in here? That's the same as 1/2 x, so the period of this is 2 pi divided by whatever's in here, which is like a 1/2 really, the x over 2. That means there's a 1/2 there. So the period's going to be 4 pi for this. Okay. So the cosine, I'm just going to draw my nice little cosine graph, and then I'll add the scaling. Pretty okay. Okay, so that's, since the period of this is 4, that's just like 1, 2, 3, 4, 4 pi, sorry. And here we mess with the amplitude, so that's 2, and this is -2. Right? Okay. And then the secant is just cosine upside down. So same game that we played the last one. Every time we hit 0 and try to flip that over, we're going to get a vertical asymptote. And then here, the thing that we're flipping over, we're multiplying by 2 after we flip things over, so 2 is still going to flip over to 2, because this is the part that's flipping over. The cosine here is still 1, and when I flip that over, it's 1, and that gets multiplied by 2. So they don't, like, cross through each other. Same game. And there's those little parabolas. Just kidding. They're not parabolas, right? They're not parabolic either. All right. What else we got? Tangent and cotangent on the same set of axes. So, what's the tangent of 0? The tangent of 0 is 0 because it's sine over cosine. And then when you get to pi over 4, the tangent function is equal to 1. And then when you get to pi over 2, you got problems because the sine of pi over 2 is 0. So now you have a 0 on the bottom of your fraction. So you get these little, like, swoopy things. And then it happens all over again. Let's see. Trying to get my scaling pretty good here. I don't know how much you like that scaling, but something like that. And these are all pi over 4s. The period of this is pi. Sorry that this one came out a little wider than that one. It's an accident. Okay, so now if we want to graph the cotangent function, we have to flip all these things over. Well, flipping 1 over and flipping -1 over, that just gives me 1 and -1 still. So the cotangent function goes through those points. But now when I flip 0 over, that's where my asymptote is. And when I flip infinity over, that's 0. So I end up with things that go through this way. So you get the idea. I'm asking you to do those in that way. It's not by accident that I asked you to do those ones together so that you could think about them together. Tangent and cotangent, that is, and sine and cosecant, and cosine and secant. All right, logarithms. Cool. So 0.5 is the same as 1/2. So log base 2 of 1/2, that's exactly the same as asking yourself, what power would you have to raise 2, the base 2, to get 1/2? Well, to turn 2 into 1/2, you'd have to raise it to the -1 power. What power do you have to raise 5 to get 625? Fourth. What power do you have to raise 27 to get the square root of 3? Well, how would you get it to be 3? To get it to be 3, you'd have to take the cube root of it, which is the same as raising it to the 1/3 power. But then after that, it's under a square root sign, so it's like you have to raise it to the 1/3 power and then also raise it to the 1/2 power, which is the same as raising it to the 1/6 power. What's the log when there's no number there? Then we assume that that means base 10. So 10 to the what is equal to 1 trillion. And that's exactly the same question as asking how many zeros are there in 1 trillion. Spoiler alert, there's 12. Okay, how do I solve an equation like this? Logarithm rules say that if I've got the same base here, I can combine subtraction as division. So that's the same as this. And there's two ways you can deal with this. You can either say, oh, okay, so that means 2, the base to this power is equal to this. So 4 equals x squared over x plus 3. You could either do that, or you could say, if only this was also in log form, you could figure out, well, log base 2 of 4 is equal to 2, so I could swap that out, and then I have log base 2 of thing equals log base 2 of thing, so the two things must be equal. Gets you to the same place. And then you got to do some math. I'm going to multiply that up to there, 4x plus 12, and then I'm going to move everything to one side because that's how you do algebra. And let's see, factor that, x minus 6 x plus 2 equals 0, so x is either 6 or -2. But this is a logarithm, so and you can't take logarithms of negative numbers. So I just better check my answers here. If I put the 6 here, that's good. That's 36, and that one's good. So -2, it's getting squared here, so that's fine. And -2 plus, so I'm good. All good. Both answers work. Should check them. That's a 2. Okay. Given that log of 5 is approximately 0.7, then approximate the following without your calculator. So let's see. How's that supposed to work? Well, log 25 is the same as 5 squared, and there's a logarithm rule that says I can move that exponent to the front. So that's the same as 2 times the log of 5, so that's 2 times 0.7 by this approximation, so that's 1.4. How about log of 500? Well, I've got a log rule that says I can split that up into this. Since 500 is 5 times 100, why would I want to do that? Because the log of 100, log base 10, that just counts up the zeros in a number like that. So that's 2, right? That's how many zeros there are. And then log base 10 of 5 is 0.7. So that's 2.7. Or the log of 1/2. Well, so the game is here, what we're really trying to do is turn everything into 5s and 10s, right? Because I know what log base 10 of 5 is, because I was given that. And if I have log base 10 of something that's just like 10 or a power of 10, that's super easy to do. Just like I counted up the zeros here. So can you think of a way to write 1/2 with 5s and 10s? Oh, you are so smart. So that's log base 5 minus log, sorry, I keep saying base 5. It's a log of 5. This is the common log, or log base 10. Log base 10 of 5 minus log base 10 of 10, because division turns into subtraction. And that's 0.7 minus, there's 1 0 in that, so that's negative 0.3. Uh-oh, sorry, there's the stuff I was doing for those. Sorry about that. All right, 0.4. Can we turn that into 5s and 10s? Well, that's 4 over 10, but that's no good. The 10's good, but the 4's not. So let's see, what else could I do? What if I went up to something, what about 2 over 5? That's no good either. What about, let's see, 4/10. I could multiply, how did I want you to do this one? He wonders to himself. So if I wanted to turn, oh, I think I see it. This is a little tricky, but if I'm just looking at that 4 going, well, how could I turn that into a 10? I could multiply by 2.5, but that's weird, because then I'd have to multiply the bottom by 2.5. But if I multiply the bottom by 2.5, I actually get 25, which is a power of 5. So that's a little tricky. If you got that, good for you. 25, that's the same as 5 squared, but the squared, that power comes out to the front like we did here. So let's see, that's 1 minus 1.4. And then last one, 625. I think we saw 625 as 5 to the 4th. So let's see. With the decimal moved over, that's the same as log 625 over 10, which is 4 times the log of 5, because 5 to the 4th power, kick that out front. So log 5, that's 0.7 times 4 is 2.8. Minus 1. There we are. And I think that's the end. I don't think there's another page of this sheet. So there you go.